CHODOSH from Stanford University. The title of his talk is Minimizers in Gamow's Liquid Drop Model.
Thank you very much for the introduction and the invitation. It's lovely to be here and see so many people. For a conference in honor of TN, I didn't have much to speak about this. Should I wait this?
You did speak, otherwise the people in the net.
That's okay? All right. Yeah, so for a conference in the honor of TN, I don't have so much to speak about, so I'm instead going to tell you something that I have thought about for a long time. I'm really fond of this problem. This is something which maybe is a bit unfamiliar to geometric analysts, so let me just tell you some of the background just to start. So first I should show you the following plot, stolen from Wikipedia, with some sort of annotation. And so if you go to the nuclear binding energy, okay, and so you look at atoms, then you find this plot where sort of this is the atomic number, right? And this is the binding energy. So it's like a energy per energy density of the atom. And so in this plot, I've drawn some various features. So, well, chemists like to draw it backwards than physicists. So, like, increasing the energy is good. Usually mathematicians like to decrease the energy. It depends on if you're talking about the atom or you, right? So the atoms like to fuse together to increase that energy, the small ones. The large ones like to fizz, so like they split apart. There's some molecule of maximal energy, right? It's not obvious if you just think about them, like, if you didn't know much about nuclear chemistry, like it's not obvious there should be some thing of maximal binding energy. And another feature is that there's no big atoms. Okay, so, well, you know that this sort of thing could potentially be modeled via the Schrodinger equation, but studying this explicitly using the Schrodinger equation is essentially impossible, right? This is much too hard of an analytic problem to, you can't make any predictions via the Schrodinger equation. So physicists started to look for some sort of simpler model. And this model was developed by the physicist Gamow, who was a famous physicist in the 30s. And so Gamow proposed the following incredibly simple model, right? So like there's no Schrodinger equation, there's nothing else. It's just a basic geometric model. And so the model says that the nucleus should be modeled by a region in R3. Okay? Let's say smooth boundary, compact smooth boundary. And the atomic number you should think of is just the volume, right? So here there's no like discrete neutrons and protons. Instead it's just one sort of like uniform mass. And then Gamow proposes that the nucleus chooses to minimize the following energy, which is the parameter of the shape plus this extra thing. Okay, so the integral over the set cross itself of 1 over norm x minus y. Okay. And so then the prediction by Gamow is that it should be a good approximation of the nucleus. So you fix the atomic number. And you try to find the set omega minimizing this functional. Okay. And so what's the justification physically from these two terms? So this term, it represents Coulombic repulsion, right? So you just imagine, you don't think about neutrons and protons, you just think about a uniform charge in your atom, right? That's a defect of this model. But you just pretend you have some uniform charge, and then of course the charges want to repel, like push apart, right? So the charges being close together makes the energy higher. Okay. So the second term is the parameter term, and this Gamow justified based on the strong force. Okay, so I think the strong force is not so familiar to most mathematicians, at least it isn't to me, but the 10-second pitch for the strong force is that it's a very local but very strong attractive force between atomic particles. So if you're very close, you're very happy to see other particles. So on the inside of your set, omega, you see like a whole sphere of nearby particles, which you're happy about. But on the boundary, you're missing half the sphere, half the boundary. So that tells you that being on the boundary, you lose out on the strong force. So if there's lots of boundary, there's lots of points losing out, so the energy should go up. Okay? So this is Gamow's justification for his model. Okay. So if you read Gamow's original paper, you don't see exactly this conjecture, but of course he's a physicist, so he doesn't state exactly what he's doing. But this model and this conjecture was kind of well understood in the physics literature since the 30s. But then it was discovered by mathematicians in 2011. And the conjecture says the following kind of striking claim. So there's a number, 3.5 something. You can compute it. It has an explicit algebraic representation. Or it's not algebraic number. It has explicit form. And so for volumes below that number, the minimizer of this energy is exactly a round ball. And then when you get bigger than that, then suddenly there's no minimizer exists, right? So any region you could do slightly better by doing some other region. Okay, so to me, like the reason I was kind of interested in this conjecture in the beginning is, well, you see that you might imagine like you can ask a lot of different types of isoparametric adjacent problems, right? There's many different ways to change the isoparametric problem. And so you would imagine that in most cases, you get some shape, like the minimizer is some shape other than the ball. But what's interesting here is like you expect the minimizer should be round. So maybe that means that the techniques we have today might have some hope to apply to this conjecture, right? It's very hard to prove something is something else if it's not a round ball. It's much more hopeful to prove something is a round ball. Okay. So V star is the number, so that if you take, like, I can write here, that's okay, all right. So if you take two balls of volume V over 2 versus a ball of volume V, right, and you put them very far apart, then, well, two balls of half the volume, the parameter goes up, but now you're saving a lot in the Coulomb term, right? The interaction between points here and point here, it doesn't contribute. And so you can just, this is like a simple exercise to see, okay, you have to compute the Coulomb energy of a ball. That's not very hard. And so you see that for precisely this volume, then you get two balls beats one ball. Okay. Notice, just a remark, that this V star, just making this definition tells you nothing about what's actually going on in the problem. All that it says is that one ball is beaten by two balls. It doesn't say that no minimizer exists, or it also doesn't say that sort of two balls are the minimizer. Like there's no information other than this exact fact. Okay, so you don't really know what's going on here. Okay, and so since this is a bit sort of adjacent from mainstream questions in geometric analysis, I'll just point out that there's a very nice article in the notices about this problem. So if you're curious, you can read the article. Oh, sorry. So, okay. So remember, oh, sorry. Yeah, so remember, I conjectured that for small volumes, the minimizer is a ball, and the large volume, there's no minimizer. And so you might call the no compromise conjecture, right? And so why is that the no compromise conjecture? So the point is the following. So we're minimizing the parameter for fixed volume. As we all know, the minimizer is the ball. That's the isoparametric inequality, okay? On the other hand, the Coulomb term actually is maximized at the ball, right? So that's the Riesz rearrangement, okay? And so if you think about minimizing the Coulomb energy, the minimum is 0. You should just take little chunks and send them off very far apart, and then there's no terms to have interaction. So what the no compromise conjecture is conjecturing is that the isoparametric inequality wins. There's no compromise between the two inequalities. Like isoparametric wins until the Coulomb wins. Right? So, okay. Okay, so just to make one last physics comment, and then we'll go to math. So this is the plot that I showed you. And so I tried to find a good chart, but you can't really find such a good chart. But if you plot the energy, like the parameter plus Coulomb of a ball of radius v divided by v, that's what this is supposed to be, and it's a pretty good approximation. So it at least has this feature where it like bends up and then bends down. Okay. And what's, I think, even more striking is that if you took a class on nuclear chemistry, which I've never done, but if you take a class, what you will learn, like atoms are described by what's something called like the semi-empirical formula. And that basically means you take the original, this is a physicist notation for the formula I showed you. They add this overall term, which actually doesn't matter because it's proportional to volume. So when you divide, it's just a constant. And then they add 2 extra terms, which are just purely made up to curve fit, right? So essentially, like what physicists are really doing, at least in a core sense, is they're taking this liquid drop model, assuming the no compromise conjecture is true, and then they're just perturbing a little bit based on this uses the idea, this is related to the idea that there's actually neutrons and protons, not just all protons. And then this is somehow like related to the Pauli exclusion principle. So, but you see really, this model, even though it came from very sort of shaky first principles, it is like kind of close to legitimately what the physicists are doing. And just another small comment, there's I think in physics, a quite famous paper by Bohr and Wheeler, and they were interested in nuclear fusion, and they really used the liquid drop model and studied the second variation to estimate the activation energy for nuclear fusion. So this, I just wanted to make the point that this model is somehow of some interest in the physics literature. Okay, so now back to math. And so I'd like to tell you what's known, and then I can tell you what we did. And so there's the no compromise conjecture. And so the first part of the conjecture is that for volumes below this critical V star, the minimizer is a round ball. And in about 10 years ago, this was proven for volumes very, very small. Okay, so like the super tiny small regime, the super tiny volume regime. And so the basic sketch of the proof is if you look at how these 2 terms scale, right? So this is like length squared, and this is like length to the 5th, because it's like volume cross volume, then divided by length. And so when length is very small, this term should be negligible compared to parameter. So you expect that this term is like an error term for the isoparametric inequality. So if you carry that out, a small minimizer is approximately a ball, okay? But now you can do like linear analysis, so like second variation at the ball, to prove that that's a strict local minimizer, and therefore anything close to the ball actually, it falls into the ball. It must actually be exactly equal to the ball. Okay. So the other hand, for volumes large, there's supposed to be no minimizer. And so Frank, Killip, and Nam proved that for volumes, well, it's not quite the sharp number that you'd like, but it's about twice as big as you'd like. If the volume is bigger than 8, then there's no minimizer. Okay? And actually, this theorem is the theorem that got me interested in this area. There was a colloquium at Princeton when I was a postdoc there. And Rupert Frank basically wrote the proof on the board in the colloquium, which tells you that the proof must be very simple because normally you would never prove something in a colloquium. And I was like, well, that's really very cool. And the proof is basically you just cut at random. You rip the 2 pieces to infinity. This must have higher energy if you are a minimizer, right? And then, but that tells you something about sort of the parameter of your cut, because that's the energy you introduced. And then you just see that if the volume is very big, that's a contradiction. So the paper is like 3 pages. It's amazing. And so I should say that there was earlier work on this part of the conjecture, but they could only sort of get extremely large volumes. So like it wasn't quantified. Maybe you could make it quantified, but it would just be like volumes bigger than 1 billion somehow. Like, okay. So there was some sort of contradiction argument earlier. Just like in the previous slide, there was a contradiction argument or like a compactness argument to say the very small minimizers. Okay. So now I'd like to just tell you briefly about the result that I have. This is with my former undergraduate, Ian Ronhumani, who's now at Minnesota. And so what we proved is that for volumes at most 1, So if you remember, V star is like 3.5. So this is like maybe not quite a third of the range. Then indeed, the minimizer is the round ball. Okay, so you see now we've gone from just a sort of a compactness argument to a genuine range. And so the interest in this result is somehow that in this result, you need to take seriously this term, right? So you can't treat it as just an error, a perturbative term, because it could be comparable size. Okay? All right. And so just to tell you what we know, so now between 1 and 8, you don't know that much. So by Frank and Nam, actually the minimizers exist in the sharp range, but you don't know their shape. And you don't know that they cease to exist past the sharp number. They might continue, if the minimizer is not a ball, it probably could exist a little bit longer past V star actually. Okay, oh, sorry. So when I started thinking about this, well, you want to prove that minimizers of this in a certain volume range are round, right? So essentially, you want to look at all the proofs you can think of for the isoparametric inequality and try to see what's going to work, right? So, well, how do you prove the isoparametric inequality? Oh, sorry. So one way, right, is direct comparison, I might call it, right? So you somehow prove that, like, you can do a rearrangement, or you do some optimal transport, or an ABP method. There's also flow proofs of the isoparametric inequality. So these are some ways of just like deriving the isoparametric inequality, maybe using the existence of minimizers, maybe not. Okay. There's also the second variation. So if you have a minimizer for the isoparametric problem, you can compute the second derivative of area for volume fixed deformations. And so this is done in the works of Barbosa do Carmo and others. And there's also some first variation based proofs. These are a little bit stranger. This is not the proof you would give in like a class on the, I don't know, in a basic class, but there's the Alexandrov theorem, which says that a closed CMC surface is a round sphere. So in particular, like a critical point in the isoparametric problem must actually be a round sphere. Okay. So unfortunately, basically none of these proofs work because like they're kind of guaranteed to go wrong because this term is going the other way. Like this term is fighting you, right? Anything good you have here is bad here. So anything you can try here, whatever the term is over here, it just goes the wrong way, right? So you're in trouble. So instead, we use the following proof, which I think is not, we're not the first person to know this fact, but no one ever really thinks about this if you think about how to prove the isoparametric inequality. So let me just tell you what our proof specialized to the isoparametric inequality would be. So suppose that you have a minimizer, and so minimize parameter for volume fixed, and then the first variation of parameter with the Lagrange multiplier constraint, like constant volume, tells you that the mean curvature is constant. And now, due to the scaling invariance of Euclidean space, you can actually compute that constant, right? In general, you often cannot compute the Lagrange multiplier in arbitrary problems, but here, using some symmetry, sometimes you can. And so you can compute that the mean curvature of a minimizer or critical point must be twice the parameter over 3 times the volume. Okay, of course, you now see this is exactly scaling because this is the homogeneity of these two terms, right? This is like length squared, length cubed, okay? So now, if I integrate this, I get that the integral of the mean curvature on the boundary is twice parameter squared over 3 times volume. Okay, it's very nice. But then what I need to do is bound this term, the integral h. Okay? And so, well, it turns out that there's a perfectly good bound for integral h. This was derived by Minkowski. At least for convex sets, the integral of h is bounded below by, this is in R3, right? There's a version in all Rn, right? Is bounded below by the following quantity. This is sharp for the ball, you can check. Okay. And, okay, this is a bit, I'll come back to that in a second. But assuming that your minimizer is convex, which is that's not a really fair assumption, but anyways. If you combine this, and you solve for parameter, right? You see, like you cancel a root parameter here, so you get parameter root thirds. You check the constants, you get this. That's exactly the isoparametric inequality, with equality precisely for the ball, right? So this is a proof of the isoparametric inequality. Okay. So I'll just say that this theorem is false for general submanifolds of like spheres in R3. So there's some, like that's well known in general, but even if you're sort of like close to round in a weak sense, there's some work first by a student of Figali, Glaudo, and then myself and Eichmer and Korber, showing that in certain ranges, the Minkowski inequality badly fails. But there are some positive results. So Guanli and Hueskin also proved using inverse mean curvature flow that, so the result of Hueskin says if you're outer minimizing, which is better than convex, then Minkowski holds. So actually, in our proof, we use the result of Hueskin at some point. Okay, so if we return to the liquid drop model, so we want to play this game, right? So you look at the first variation, you compute the Lagrange multiplier, you integrate it. So one term that we get is the mean curvature coming from parameter, okay? And so the other term that we get is exactly, if you differentiate this as omega varies, then what you end up with is actually the derivative falls onto one of the two omegas, and then you get a boundary speed times this. So you actually get this term. And the analog of the Minkowski inequality is bounding this term. So it looks very similar to what we had before, except you're only integrating over the boundary. Okay? The 1/2 disappeared. And so now what you need to do is to prove a sharp estimate of this from below, just like Minkowski. But in some sense, morally, it's going to be a wrong way estimate, right? So it's always dangerous to prove things. Like you expect not to be able to prove such an estimate because you know that you can't prove that like the isoparametric theorem with Coulomb replacing parameter. That's the opposite of what you get, right? So okay, but what you can do is prove the following. Maybe I would call it a wrong way estimate. It says the following. So this is the analog of Minkowski. Minkowski had integral h bounded below by something, so that's sort of good news. And this is what we proved. And this, okay, it's not obvious if you unless you're much faster at me than integration. But you can check this is equality for the ball, right, if you're bored. Right? Okay. That's just an explicit integral. And so in some sense, the reason that you should be allowed to do this is because the parameter term shows up, right? So it's not completely a wrong way inequality because now parameter is somehow playing a role as well. So you're not just proving the first variation of the Coulomb energy is bounded below at the ball. Okay. So how do you prove this? I think I have a time to just tell you. So in some sense, this fact was kind of the first thing we proved, but using a somewhat surprising method. So the proof involves integral geometry. And so in integral geometry, you can look at the set of inwards pointing unit vectors on the boundary and write L for the amount of time that the geodesic flow or the straight line lives in the set. It's okay. It's okay. And then you can relate this integral just using polar coordinates, right? This is nothing more that around each point on the boundary, you do this integral in polar coordinates. Well, because your set is not necessarily convex, you might miss some part when you do the polar coordinates. Like I only do the first piece of the integral. If I stop, then I don't keep going later. So, but that's a lower bound. That's the direction we want. And that's equal to this term. And then, using Santelow's formula, you can look this up, it's in integral geometry, you can bound in a sharp way integral LU squared. And then carrying that out, I won't subject you to the analysis. It's not very hard if you know what to do. You get this inequality. And so, yeah, just to explain briefly sort of how this all fits together, and then I'll stop. So again, the first variation of the energy, instead of integrating mean curvature over the boundary and using Minkowski, we integrate the first variation, which is mean curvature plus this other term, and combine Minkowski in the wrong way inequality. And so I'll just say, it's not trivial to justify that Minkowski holds, right? It fails in many situations. So you have to prove that the Minkowski inequality does hold for this set. That's a technical feature that takes some serious work. Okay. If you do that and use the fact that you have a minimizer, you get the following expression. So okay, I don't expect you to follow that calculation, but what I just want to say is you get some expression for parameter. You eliminate the Coulomb energy from everything. And now this is some sort of like, well, it's not exactly a polynomial, but it's some sort of polynomial type inequality for parameter. But you know that the parameter is bigger than the parameter of the ball. So this is some function in terms of parameter. And then, well, you can just check that when v is less than or equal to 1, the only solution is when you're equals to the parameter of the ball. Everything was sharp on the ball, so you know that the ball was a solution. And then you just look at the plot, right? For v less than 1, it goes the wrong way. So there's no solution, only this one, right? And so then using this, you just see the only possibility is the ball. So that finishes the proof. All right. Okay. So I'll stop here, but just to say happy birthday to Tian. So yeah, thanks for having me.
Questions?
So I have a question about, like here you work on like 3 dimensions.
Yeah.
How about in high dimension?
Sure. So I know I never checked this, but I think you can study like parameter plus 1 over x minus y to the n minus 2, right? That one. But people also study to the alpha, right? That's not. I mean, okay, it's fine. And so I think our method should work for alpha equals n minus 2, but no other alpha. And that's kind of a mystery. So in some sense, we just get extremely lucky that we can prove it for the physical alpha. Okay. I don't know why it works, but it only works for that. I think this should work. No one ever wrote it down. I tried to convince an undergrad to do it, but I haven't gotten them to do it.
So do physics also expect that true for like other alpha?
Yeah, sure. So there should be a corresponding conjecture for in all dimensions for other alpha. Even people have studied like this, like in the very small volume regime, you can even study like non-local parameter plus the alpha repulsion energy, maybe plus some other terms, and it's still true there. So yeah.
Thank you.
Yeah.
Other questions?
So Otis, so this minimizer, you say on some transparency, you say it's a minimizer always exists.
Oh no. So it doesn't exist. Let me see. Oh, it doesn't exist past volume 8. We know that.
Okay.
And so you don't. But you actually, it's proven that it exists up to the critical volume. But we sort of can do like a continuity argument to prove the minimizer exists. So like you work up to the first time where the minimizer is not a ball, and then at that volume you do your analysis, and if it's in that way it's enough. It gives you enough information to prove the minimizer does exist. It's just some other shape.
I see. So one minimizer does not exist. I guess in the conjecture is. If a V volume is strictly bigger than a V star, this critical value, then minimizer does not exist. So, but you can always try to minimize this function, right?
Sure,
so this there might be a limit. A limit might be breaks up or.
Yeah, that's right. Like I think you
What's
could conjecture. you could conjecture that the minimizer is always a union of some number of balls of equal volume infinitely far apart in some generalized sense. I think that's probably the real conjecture. So, well, we can't even get to the first breakup, but I think in all volumes, it's probably true that you're always just some balls far apart at infinity.
And maybe for volume sufficiently big, you can see how these things how the minimizer breaks up in the limit, right?
Yeah, I have maybe more of a curiosity. At some point in the proof of the isoperimetric inequality that you showed, you said, okay, let's assume that omega is convex. Do you know if there is like a simple way from dimension 3 above to show directly?
No, I have no idea how to prove that. Like, what is simple is to prove it's outer minimizing.
Yeah. It's mean convex, outer minimizing.
Yeah, mean convex, outer minimizing, and that's exactly what you need for the Huyskin.
Okay.
So yeah, I was just lying a bit, but convexity, I don't know. Like, we prove that minimizers below a certain volume are outer minimizing. Even past one is not one doesn't obstruct the Minkowski inequality. Really, you could go up to almost 2 to get outer minimizing. But yeah, I don't think it's clear how to prove convexity.
Okay. Yeah. Thank you.
Any other questions? Yes.
Thank you. Since you're comparing strong nuclear forces with Coulombic forces, the strong nuclear forces always overwhelm the electromagnetic forces. So it's always going to be held together. So I wasn't quite sure how this model works.
I think that okay, I'm not a physicist, but I think the strong force is much stronger, but has a very, very short range.
Yes, exactly.
So, and I think that if you get far apart, the strong force is not relevant.
Right, but you don't. That's what holds the nucleus together to begin with.
Well, okay, in this model, it's still acting only in this, I mean, you have to ask Gamow, right? But it's still only acting in a very local, it's not acting even among the whole nucleus, just particles very close, nearby in the nucleus is his.
Right, and that could be in your perimeter term too. You could put, there is nuclear models where it's like e to the minus alpha over an x minus y term.
Sure.
So the question is, why don't you just put that in? Then you can actually integrate, get the total the total nuclear potential of that force and compare it to the potential of the Coulomb force over the whole sphere.
Well, that's probably a more refined model than this. Right? This is just a sharp cutoff.
And the Wheeler-Bohr model, it does that, so then you could get these dumbbell-like performances.
Yeah, but they're actually using the parameter.
What?
Bohr and Wheeler are using the parameter.
Right, but they get a dumbbell, they get a splitting of the atom. That was the point of it.
Sure, but it's with the same model.
But I don't see how you get splitting here or
because we're talking about minimizers. They're talking about like a mountain pass, like a bifurcation or a mountain pass situation.
Yes.
So yeah, it is actually the same model that Bohr and Wheeler are using.
I see, but they use the nuclear forces inside the.
Well, they don't use. I mean, they just use this model. They don't use any physics beyond this model.
They use this perimeter model.
Yeah, exactly. Yeah.
Okay.
Yeah. Maybe there's a section where they do something else, but in the main part of the article.
I thought the whole idea was to model splitting of the atom, actually.
Yeah, using this model, they model the splitting of the atom. Yeah.
Thanks. Any other questions?
So if you knew that the minimizer, if it existed, it is convex, would it be over? No.
Not for me. Maybe someone else. I don't know. Like you could study this functional among convex regions. I think maybe someone has done that. And then a minimizer should always exist because you can't split. But I don't know what they can prove.
But would it be the same threshold for the convex problem?
No, I think so. The ball is a local minimizer for a longer range than it fails, like it's still a local minimizer for longer than it fails to be the global minimizer. So presumably it's in the convex regime, it's the minimizer for a long time. Maybe it's always, I don't know if it's always the minimizer, or no, it probably isn't. Like I think at some point you can deform it slightly in a smooth way that preserves convexity so that to push the energy down because it fails to be a local minimizer. But I don't know if you can say anything more like relevant than that.
Thanks. More questions? If not, let's thank the speaker again. The next talk will be at 11:30.